Welcome back, everybody. The next presenter will be Travis Goodspeed from Tennessee, presenting the assembler for ROM recovery. Say hello to Travis.
Howdy, everybody. So I have a thing where I do not drink before my talk, but as Tony May reminds me, it is no longer before my talk. Just by a quick show of hands, who here has used assembly language or in any capacity, either writing assembly or reading assembly? Fucking awesome. Okay. So who here has been mad at their assembler because the piece of shit didn't do what you wanted it to do and you couldn't quite figure out why? Okay. So about a third of you are raising your hand and 2/3 of you are liars. 2 years ago here at BalCCon, I did a workshop on mask ROM photography. In the workshop, I gave all of the students a photograph of the microchip that is in the Nintendo Game Boy from 1989. And from that photograph, the students extracted the boot ROM, which is the code responsible for showing the Nintendo logo at startup and making sure that the Nintendo logo is in the game cartridge. This is how the copy protection works on the Game Boy. At that workshop, if you wanted to, you would get the bytes, but if you wanted to disassemble them, you needed to install either Radara 2 or MAME in order to have a disassembler for the SM83 architecture. And both of those disassemblers work, and both of them support a wide variety of architectures, but you have to install them separately, and they don't have assemblers that exactly match their disassemblers. And if you want to add a new language to them, it's a lot of work. And I found myself recovering other mask ROMs and writing machine code for these microcontrollers. And I found that I would get frustrated with the tooling because I would be excited about today's project. And I didn't want to take a detour to add a new language support to a large project that might take me a lot of time. So I had this idea for an assembler that would be very fast to retarget. You should be able to sit down in a cafe and add support for a new architecture, say an 8-bit architecture. You should be able to add support for that in an hour or two so that you're not taken too far away from the project that you really want to do, just to get good tooling. Your assembler and your disassembler should come from the same definitions. There is no reason to write those as separate tools. There's definitely no reason to maintain them as separate tools. And the parsing should be shared between all languages. For those of you, show of hands, who has written code, a parser in like Lex or Yak? Bison? Okay. Doing that is something that you can learn to do. Doing that for a dozen languages and keeping them in sync with each other is something that you should never have to do. I have a single parser, it is shared for all languages. And when you're making an assembler, it is very easy to fat finger the keyboard, to type in the wrong byte here or to copy and paste something from another instruction. But you can do ruthlessly effective self-testing. You can have the software run through and make sure that no two instructions overlap, that there's never any ambiguity in what something should disassemble to make sure that if you take your whole program and you assemble it and then you disassemble it back, that you get the original. And also, who here plays around with like Duolingo or those apps that let you learn a foreign language, right? Okay, so I wanted something like that so that when I was learning a new instruction set, I could tinker around with it in order to figure out if what I was saying would work. For example, most CISC instruction set chips have jump instructions, but you always forget what flags they are. So I have an interactive mode where you hit the J key and a tab, and it shows you every instruction that begins with J and what the parameters are. It'll also auto-complete things like symbol names for you. And today's lecture is going to tell you how I built this, how you could build something better than this, and if you would like to play around, the GitHub URL on the screen has the complete source code, and this is also integrated into MaskROM tools. So if you attended my workshop 2 years ago, updating to the latest MaskROM tool already gets you a binary build of this. Bit of my own background, I started a hacker magazine called the International Journal of Proof of Concept, or Get the Fuck Out. We've published 22 releases across 4 or 5 continents. We have 3 bound collections through No Starch Press that you can buy wherever fine books are sold. I wrote MaskROM tool, which is a CAD program for recovering the read-only memory of a microchip from photographs of that chip. And most recently I came out with a book called Microcontroller Exploits that is a collection of every way to rip out firmware from a microchip when you're not supposed to do so, but you want to do so anyways. Here's an example of MaskROM tool. If we zoom in here, these are bits in the Game Boy. These horizontal and vertical lines are crossing wherever the bits should be sampled. There are a couple things to note here. This is not a perfect grid. The rows come in pairs. And the columns are grouped in sets of 8. And it's very important to understand that these 8 bits, everything that you're seeing in this photograph is 1 bit of significance. We're seeing all of the least significant bits here. You're not going to read the bits left to right and get the byte in order. It's going to be spread across the full width of the ROM. With my software, I can then identify that the black spots are a 1 and the white spots are a 0. If you zoom in really closely, you can see that this is a vertical metal connection. And the 1s are formed wherever the 2 layers are connected to each other, hence the dark spot. And the 0s occur when they are not connected. So it's basically like a working transistor for a 1 and a broken transistor for a 0. From that, you can get the bits in physical order. And a very valuable thing is to be able to disassemble them. Along the way, you have to figure out what the right ordering is. And you also have some complications like damage. Pictures are not perfect. Sometimes there are stitching artifacts where, I don't know, maybe I bump the table while my microscope is taking these pictures. Or maybe there's a speck of dust because my lab isn't a clean room. I wanted to be able to work around them. You also have this asymmetry between disassembler technology and assembler technology. For disassemblers, we have IDA Pro, we have Ghidra, Radara 2, Binary Ninja, a few that I've forgotten to mention. These have flashy GUIs. They support tons of architectures. Like IDA Pro will disassemble everything if you have the full commercial license. They even have lifters and decompilers. So when I'm reverse engineering code and I'm too lazy to look at the assembly language, it can give me what is usually pretty reliable C code, allowing me to read it at a high level or even copy and paste it into another program. On the assembler end, we've had a lot less progress. The best of them these days are NACM assembler, and various macro assemblers. These generally have a scriptable command line, and they have preprocessor directives and stuff like that, but there's no major feature that these have that didn't exist in assemblers 20 years ago. You also have breaks by instruction set. So NACM is a great assembler, but only for x86 and AMD 64. It's kind of useless if you're doing Z80. And what a lot of us do when we're trying to write machine code in a weird language is we'll do it with pen and paper. And then we'll use the DB directive in NASM in order to have bytes and comment on those bytes. And we shouldn't be doing that anymore. So good ASM is my assembler. It is ridiculously easy to retarget. We're talking 2 hours in a cafe from beginning to end, adding support for a new 8-bit CISC microcontroller. Sometimes you wind up with an instruction set that is pathologically difficult to describe, like x86. That does not apply to the 2-hour prediction. But for anything with, say, 300 opcodes or less, you should be able to do that in a couple of hours. The assembler and the disassembler are formed from the same definition. So I'm not writing them separately. I'm not defining things specific to one direction. What I'm doing is I'm describing what the opcode and the mask of that opcode are, and then I'm describing the parameters in order along with their masks, and any grouping symbols or decoration around it, so that at the end, that one definition works for both assembly and for disassembly. I have a shared parser for all languages. I do not have any parsing code at all that is unique to a specific language. If you have a construct that is used by one but is not used by another, that's fine. You just make it part of the global definition, and you avoid using it in the languages that don't support it. This builds in many different ways. It works as a C++ library. So when I'm working in my CAD software and I need to take the output of the photograph and convert that to the disassembly, I'm calling that as a C++ library. I'm not shelling out to a command shell, I'm not calling system, and I'm not wrapping it in a shell script. Everything is immediately available. You'll see in a bit how that's useful for things like tracking damage in the photograph. I also have a command line interface, which is what you would wrap in a makefile to actually build and run and test your code. And I have a REPL interface for both the assembler and the disassembler for toying around with the language. So you can pop this open on your command line. You can do tab completion for the verbs, for the mnemonics, the names of the instructions, and for their parameters. You can export commented byte files. So I was writing a smart card exploit a few years ago, and the smart card exploit consisted of a Golang program that would load 6805 machine code into the smart card and trick the smart card into running it. And I wrote that by hand because I didn't have a good 6805 assembler, and I've now rewritten that using this assembler. One of the cool things that this assembler can do is it can output to legal Golang code as a byte array with comments explaining the bytes, and with all of my symbols exported as a hash map, so that my Go code not only has the bytes available, but also can refer to particular offsets in the program to, say, touch up an address or to do a little bit of relinking at the very end. And I have full integration with Mask-ROM tool and with like an iPhone and Android app as toys. If you need to pull this into another program to understand what machine code does agnostically, you can do that through the library interface without having to shell out and without having to script anything. As a quick example, I was on a bus recently. I was going from Boston, Massachusetts to Hanover, New Hampshire. And on the bus, I got really nostalgic about Texas Instruments graphing calculators. In the 1990s, Texas Instruments made these things, and they would give them to school students. You'd have it in like 8th grade or high school. And you could program them in BASIC. But the teenagers got really clever. They figured out that there was a custom menu. These are the function keys at the top of the keypad. That is implemented by a short string to describe what the custom item does, and a function pointer to a menu handler. And if you take a backup of the calculator to your computer, you can change that pointer to go somewhere else. And then they figured out that the screen buffer is at a perfectly predictable address. Like what you see on the LCD, that is a buffer in RAM, and it's executable. So they changed the pointer in order to execute the picture, and that was how they got remote code execution on this calculator, so that they could get video games like Mario or Drug Wars or whatever is a good example for the children. I wanted to play around with this. I wanted to reverse engineer the ROM. I wanted to write my own program for it. So on the bus, I defined another language for my assembler to support the Zilog Z80 chip that this calculator used. This code is the example of the no-op instruction. For context, this is inside of a C++ class constructor, and there are a couple of preprocessor definitions to keep things short and sweet. The NNEM function is creating like the skeleton of our instruction. It's saying that the instruction has a name of NOP, that it is 1 byte long, that the value of that byte is 0, and that the mask of the value, meaning like which bits matter, is FF. So all of the bits matter. This instruction has to be 0, 0. None of it can change. It also adds a help entry saying that this is no operation. Help is important because you're going to forget the details of a language while it's new. And an example instruction. In this case, just NOP, because there are no parameters. The example is used both for, as an example in tab completion and also for self-testing. So when the thing runs the self-test, it's going to have NOP, and it's going to make sure that that becomes the byte 0, and it's going to make sure that it does that by matching this instruction and no other instruction in the definition. And sure enough, from the command line, I can type NOP, and it gives me 0, 0. Or I can type 0, 0, and it also tells me that NOP is 0, 0, by giving me the listing back. A more complicated instruction would be decrement. Decrement has a value of 05 with a mask of C7, because some of the bits in this instruction are the opcode, and some of the bits are the parameters. And as they're mixed, the masking was what allows me to tell the assembler which of these bits I care about and which of these bits are a parameter. I still give it a help entry. In this case, I'm saying, actually the help entry on this one is wrong. I'll correct that later. The example entry that I'm decrementing the B instruction, or the B register. B is one of the 8-bit registers on this architecture. And it could be registers other than B, but B is the one that I use as an example. And then I begin loading my parameters in. I tell it that I have a Z80 8-bit register, and that it has a mask of 3.8. And if I take C7 and I bitwise OR that with 3.8, what do I get? Somebody call it out, please. FF. And if I bitwise AND them, what do I get? 0, 0. Those sorts of self-tests allow me to make sure that all of my bits are defined to be something and that I haven't accidentally forgotten any. It also allows me to make sure that I haven't accidentally overlapped them and defining them in the wrong location. And it will also compare that against other instructions to make sure that no two disagree. And sure enough, I can now type in my instructions, and if I decrement the B register, that becomes 05. If I decrement the A register, it becomes 3D. If I decrement the H register, it becomes 2D. And very quickly, you can imagine how this would build up to a complete definition of the language. Some instructions have more than one parameter. I handle that by just chaining in more parameters. I can also insert a parameter group and specify what grouping symbol I'm using. So like maybe I'm using the round parentheses, or maybe I'm doing the square brackets. All of that can be supported, and I can mix them, I can nest them, because the parser that is handling them is nothing that I have to write for implementing this Z80 language. It's shared with all of the other languages that are already implemented. Sometimes you have conflicts. Like in Z80, for example, you have this @HL register, and it's special. It fits in where an 8-bit register would be. And it says that I want to take not the value in any register, but I want to take the value in memory at the H register followed by the L register, and I want to grab the bytes that's there. The prioritize line here tells my assembler that the second instruction is the winner if there's ever a conflict. And you can also specify a hierarchy. You can give it a number, whatever priority you want. But the important thing here is that there is a clear winner, and therefore there is no ambiguity as to which bytes would win or which of these instructions should replace the other. At the end of it, I can then write a complete program. I can, the first line tells the parser that the language is Z80. This is great because it means that I don't need a command line parameter to specify what my language is. I have one, but I don't need it in my make files to clutter things up. .org 0, I'm starting at address 0. That's where I'm beginning. Here, that's a little bit of a lie. In this architecture, you don't really know where your code is going to run from, because you're running inside of a heap, and the heap is garbage collected. And during garbage collection, variables get moved around. And the program that sits within the video memory is looking through the rest of memory to find the other programs to run them. And therefore, when it runs your program, you don't know where you are. You can do relative addressing, and that works fine, but you can never refer to your own stuff by an absolute address. .db hello people, comma 0, that's a null terminated C string. That's the same on pretty much every architecture. So there's no need to make a definition of that unique to Z80. Call ROM call. This is a function call. And it's kind of a normal convention in 8-bit microcontrollers that you'll have a function that will look at the return pointer, dereference it, and post-increment it, so that the parameter can come as a byte afterward. And here, when I have clear LCD, that's coming in as a data byte, just like it would a string or a number, but it's defined in a header file. The end result of this, you want to run on the calculators. At some point, you have to export it. So you build your program. This is it as a flat binary file. This is what most assemblers would give you as a flat file, and then they would also allow you to do, say, an ELF file. For microcontrollers, ELFs are fine, but you generally want other file formats as well. For example, you might want a listing. So this listing allows us to see what all of the bytes would be that the assembler puts as output, while also seeing the source code in the comments in order to make sure that we didn't make a mistake somewhere. Or if I'm trying to debug my program and I see that it's crashing at a particular address, this will let me see what that address is. As I said before, many of us use the netwide assembler, and we do it with the db directive to include bytes, and then we comment what those bytes mean on the side. I can also output that file format, which means that I can give you the commented code in a style that you can make small changes to without your having to have a copy of my assembler or having to know how to use it. So if I have a friend who's great with Z80 but doesn't know my code or care to install it, I can share a file that my friend can change and send me back changes and can work with even without any custom tooling. I can output to Golang. This is a hash map of symbols at the top, followed by a byte array of the bytes at the bottom, complete with all of the assembly code and commentary so that I know what each individual line does. As another example, I have this card here. This is a DirecTV F card. There is a company called NDS, and they made smart cards for television services the world over. This was one of their North American cards, and internally it's an MC68HC05SC1, which is a really fancy part number that means that it's a 6805 chip, but the smart card variant. And the smart code variant has hardware scrambling. The opcode is rearranged, but only the opcode byte. The parameter bytes of the instruction, everything after the first byte, they're left in their natural order. And data is never scrambled. So if you read a byte as data from code memory, you get the byte as it is and not like a scrambled version of it. So Chris Gerlinski sent me a little tweet telling me how the scrambling works. And this is his full definition. He says that only the opcodes are scrambled, not the operands. The bit order from most significant to least significant is 7, 6, 4, 5, 3, 0, 1, 2. And then we're XORing it with 0x80 in order to flip the most significant bit. He got this from a mailing list in 1995. And he also points out that if I look at the chip really closely, I should be able to physically see the scrambling. So this is a C function to do the scrambling. This is used by my F-card module. So I'm inheriting from my regular 6805 definition, and then I'm scrambling the opcodes in order to make it work differently. And this also means that if I fix a bug in 6805, my bug fix already applies to my F-card implementation. And if I rewrite my 6805 module, I can make a similarly inherited class to do the same scrambling on the new 6805 module, so I'm not backed into a corner for old code. I then looked at the chip. What you see those horizontal lines in about the middle of the picture? That's the data bus. That is the byte that is fetched out of memory. It runs over those wires. And if I zoom in a bit, you see that beneath those wires, there are vertical lines. So those vertical lines, if I zoom back out, go into this piece at the bottom of the picture, and that is the instruction decoder latch. The job of that latch is to hold a byte in memory in like a little buffer so that the byte can be decoded to do whatever the instruction says it should do, and to only replace that byte when the next byte for the next instruction needs to be fetched. So if you have a 3-byte instruction, this will hold only the first byte, and will hold it until you move on to the next instruction. And again, horizontal lines bring the bits in, the vertical lines beneath them bring the bits out. And if you look really closely, you'll see that there are some black circles in there, which are vias, which we'll get to in a minute. These are the bits in the column order that run out to the instruction decoder. And these are the input bits that come in from memory. You'll note that there's like an extra unused one at the top. I think that's a ready line or something. I haven't reverse engineered that. But what I have reverse engineered are these little circles here. And what those circles do is they connect the row to the column. And on a regular 6805, these are completely diagonal. But on this 6805, they're in the wrong positions. And the ROM on this chip happens to also be encoded in the VIA mask, which is important because it means that when you change the VIA mask to change the read-only memory, you can also change the VIAs in this part of the chip in order to change the opcode scrambling. So if we really wanted to, we could have a compiler that would change the instruction set every time we made a new mask revision for the chip, so that different versions of the chip would use different scrambling. Now, Chris also sent me an example exploit for this chip. In the style of smart card exploits from the 90s, the exploit is delivered just as a string that is a bunch of bytes. And it will even tell you by the protocol what the response is. So first you send a 5-byte header, then it sends back the byte 42. And if it sends back 42, you send it these 92 bytes, and it gives you the 3 kilobyte EEPROM in reply. Why were these exploits so focused on dumping the EEPROM? Yes?
The keys for the descrambling are in there for the directive feed.
Exactly. The keys for descrambling were in that EEPROM. In later generations, they started using an ASIC so that the contents of EEPROM, along with the contents of ROM, would not be enough to emulate the chip. But in this generation, if I give you those 3 kilobytes and also a copy of the ROM and an emulator, your PC can accurately emulate the card and decrypt your television signal, which means that 2 or 2,000 or 2 million people can watch the same encrypted television feed without paying for it more than once. Because my F-card definition is inherited from my 6805 definition that already works, I'm able to disassemble these bytes just by pasting them in. If we zoom in a little bit, take just a second to read this code, and I'd like you to speak up, just blurt out and loudly if you see something in here that tells you that this is real code. This is real code, that's not a trick question. But when you look at this, how do you know that it's real code? What do you see in here that you would not see if we disassembled random numbers or line noise? Yes?
Chunks with the similar instructions.
Exactly. We have 2 JSR instructions, one at 0D and one at 10. And these are going to 2 addresses just beneath 2000 hex. And in real code, it is normal to see jumps to areas that are near each other. Because, for example, those addresses I happen to know elsewhere are part of the mask ROM. So what this is doing is it's calling into functions in the mask ROM. JSR in this instruction set is jump to subroutine. So it's jumping there, and then it's returning back from there. What else stands out here? What else makes this look real? I don't have my glasses on, so you might have to just blurt it out.
There's branch after comparison.
The X variable perhaps?
Sorry?
The X in the frame at the right side.
The X at address 0?
The X is a variable at the very first instruction.
The very first instruction. X in that case is a register and not an instruction. But the use of A afterward. If you look at the second instruction, LDA at 0x88, and then we increment A, and then we store back to 88, that's taking a global variable from 88, putting it into the accumulator, adding 1 to it, and then storing it back to the global variable. That's part of a loop. And these NOPs at the end. This is a NOP sled. You use this when either you want to keep padding in your program or your landing location is a little unreliable and you need to support it wherever it happens to land within the sled. So I have that. I have the jumps that were called to the end of ROM. And then I also have this global variable being loaded into the accumulator, incremented, and stored right back. One of the things I'm trying to figure out, and I'm making some progress in, but I'm not doing great yet, is I need lots of these tricks for figuring out when code is real, because that tells me when I've discovered the correct ordering for the code within a mask ROM. Because it could go left to right, it could go right to left, top to bottom, could be interleaved, could not be interleaved, could be paged, could not be paged. I can enumerate through all those configurations, but I need the computer to recognize by disassembling all of the permutations which is the correct permutation by having features like this. I've figured out how to do this for any particular language that I sit down and care to. I have not yet figured out how to do this generically. It's possible that that would require a lifter. It's possible that it does not require a lifter, and I haven't figured that out yet. The other thing that I can do is I can take this code, dump it out, and begin editing it in order to understand it in emulation or work with it elsewhere. So as part of figuring out the order, a ROM generally has a native size. So an 8-bit ROM, when you read from it, you assert the address lines, you tell it you're doing a read, and it gives you back 8 bits. A 32-bit ROM does the same thing with 32 bits. When you fetch this word, Sometimes some of the bits aren't used, like a PIC16 054 has 12-bit instructions but 13-bit words in the ROM. I think it's because they reused the ROM from the wrong chip. There are rules to it. Like your most significant bit will be on one side and your least significant bit will be on the other. But the rules get jumbled up a bunch, and there's no physical reason why the rules can't be violated on any particular design. This is the ROM from the Clipper chip. In 1997, the American government decided that Americans deserved encrypted telephone communications that only the American government could hack into. So they released it with a backdoor. The backdoor works by having a symmetric key that is unique to each of these chips. And that symmetric key is matched to a serial number. When you make a telephone call, the serial number is divulged, encrypted with a family key that the other device will check, so you can't just block that out of the packet. And then if law enforcement wants to, they can use a warrant or skip the warrant or however it would work bureaucratically to get a copy of your symmetric key to be able to read the divulged copy of your session key. My grad school advisor, Matt Blaze, played with these things in the 90s, and I really wanted to get a copy of the code out of them to understand how they worked. This is a photograph of the code that I took in my lab. I can, of course, mark it up in MaskROM tool because I have the software to do this. As I zoom in, I'm able to get all of the words out. This is the accurate decoding in Little Endian. It's a weird thing about ROMs that they don't actually have endianness because you're always fetching at a word size. And endianness only exists when you're able to read the same thing as both bytes and something larger than a byte. If you're only allowed to read in one size, it is neither big nor little endian. You just have to pick one to represent it as a file. Now, the way that I figured out the ordering for these instructions was I spent a week in Bogota, and I had a notebook, and I was scribbling all the different attempts in the notebook and writing Python code, and I think the hotel staff thought that I was out of my mind, but at the end of it I got the ordering right, wrote a module for it, and that's how my software supports it. What I'd much rather do is have this work automatically, which I now have, and the software can correctly solve for this. And the way that it does it is by this little condition field on the far left end of the instruction here. On the chip, the condition field is on the right side because the most significant bits are on the right end of the chip. And if you look here, you see that the rightmost big column is kind of light colored in aggregate. And the column to the left of it is split with a light side on the right and a dark side on the left. On this chip, the light sections are more ones than zeros, and the dark sections are more zeros than ones. So what we're looking at, counting from the right, is 1110, which is an E, which is the condition code for unconditionally executing the instruction. When you reverse engineer 32-bit ARM code, you'll notice that the most significant nibble is almost always E. And this is why, because it's almost always executed. And that is the tell that allows you to figure out the ordering of the bits on this chip. You can see the same thing in the disassembly, that almost all of these instructions begin with an E. And the exception here is a branch not equal instruction, which is conditional, and it comes right after a comparison. So when you're reading this code, you'll find that not only does almost everything begin with an E, but the things that do not begin with an E almost always come after a comparison instruction. And that's how you solve it on the ARM 6th generation. Now, every instruction set has a different way to do these tells, and some of them are quite hard and some of them are quite easy. For example, some instruction sets are very sparse. Most opcodes are not defined, so if most of the instructions you see have legitimate opcodes, then it's quite likely real code. Others, like 8051, define all but one opcode. Everything in 8051 except for A5 is a legit opcode. And A5 is used in some vendor-specific chips. So on those, you're not able to do the trick of just checking to see if the instructions are real. There's also a word ordering problem. We need to figure out which order the words are placed in. And if we get it wrong on a RISC chip with 4-byte instruction words, all of our instructions still look legitimate. So here, I have one ordering on the left and another ordering on the right. Can someone tell me by looking at this which is correct and which is wrong? Today on ARM, your interrupt table consists of handler addresses. So today, if you look at an ARM Cortex-M3 microcontroller and you dump its firmware, you will find that the very first address is the reset vector, and the second address is the stack pointer, or maybe I flipped those in my head. And you'll find a whole bunch of 32-bit numbers, all of which are odd because they're thumb instruction set, except for the stack pointer. And you'll find that all of them are in code memory, except for the stack pointer, which will be in RAM. This is an older version of ROM, an older version of ARM. And back when this was made, every program would begin with an interrupt table made out of instructions rather than addresses. And those instructions would usually be branches to where the handlers actually were. So looking at this, after becoming familiar with the problem and the architecture and all that other stuff, I can see that the one on the right is the correct ordering. And I can do that because each of these is a branch, that all of the targets are in roughly the same region, and all of them are 4-byte aligned. Why does it need to be 4-byte aligned? It's not stack alignment, it's, yes. Instruction length alignment, yes. So this is old school ARM. Every instruction is 4 bytes long. Therefore, every instruction needs to be at a 4-byte divisible address. Z80 has its own tricks for this, but I'm going to skip past that in order to get to some other features of the assembler. If I give you a piece of malware to reverse engineer, or if I give you a legitimate program, you usually get a perfect copy of it. If you have damage to it, it's either because maybe I'm getting it from a core dump and I'm not able to reproduce it, and the damage is usually regional in that. On a microchip, when I'm photographing these ROMs, I'm very often getting dumps that have dust on them or have chemical failures. So on this chip, I've got my ones and my zeros. Wherever you have the big circle, and the big circle has like the line above it, that's a 1. And if it doesn't have the line above it, that's a 0, and the same below it. But this black spot, I have no idea what bits are beneath this. I can figure out where they are, how many there are, but I have no idea what the real values are. So my tool supports marking these as damaged and forwarding that to the assembler, so that the assembler can then show me which fields it's not quite sure of. Maybe a parameter is wrong, or maybe the opcode is wrong, or maybe it's a don't care field and I don't need to know one way or the other. This is particularly important because the bits of significance are regionalized, which means that like all of these damaged bits here are in the same bit of significance. 1 bit per byte, which means that in a 1-byte instruction, I basically have a left or a right. Like this is a jump instruction or this is an add instruction. And if the code is clean and my damage is small, I can figure that out manually in order to work around the deficiencies in my picture. Here's an example of a chemical error. This is a Game Boy Tamagotchi toy. If there are any parents in the audience, I don't mean to frighten you, but this Game Boy game would beep in the middle of the night to wake the kid up in order to feed the Tamagotchi. If you're ever really pissed off at a cousin or a brother-in-law, you might consider getting this game. Here I've got a disassembly of these instructions, and I've displayed a map of the damage within the disassembly. So the 1 bits show me which bit I don't trust within that dump in order to work around it or to figure out the meanings of my error. If you'd like to play around with any of this, this would be the slide to photograph. MaskROM tool is the tool that I use to take a photograph of a chip and work my way backward to the bytes. It now automatically includes good ASM, which is my assembler and disassembler. Nipper tool is the exploit that I wrote for the old smart card, and GB-ROM tutorial is the one that we went through here at BalCCon 2 years ago as a workshop in order to recover the boot ROM of the Game Boy from photographs of the chip. And if you'd like to learn more tricks in this style, I have a book out through No Starch Press called Microcontroller Exploits that consists of, the first half of the book are fully worked examples for how to hack into these chips. And then the second half of the book is just an encyclopedia. You look up part numbers in the index and it tells you how to hack into them. And that is my assembler, and thank you kindly for your time and attention. Yeah, I think we have a bit of time for questions. And these fine folks will run around with the microphone, and they will cut us off when we've run out of time.
We have 10 minutes.
We have 10 minutes. Who has a question?
Yeah. Thanks for making me feel dumb. I have a very shy question. I'm afraid of being nerd sniped or something, but so when I mostly know x86 assembly, and I know there are 2 notations, Intel and AT&T, and I was just wondering if your tool could handle different notations, and if it's, because I don't know anything else, so like microcontroller, if it even is a need for it, for different notations.
Right, so there very much is a need for different notations. The need is that a lot of these instruction sets were written before we had standard software. So a lot of the documentation explains what the opcodes do, what the parameters mean, and where the parameters go, and it does not tell you what order they go in. Sometimes there's a convention that we describe all of the registers, source and destination, and that we put, say, the source later in the instruction and the destination first in the instruction. When Intel and AT&T wound up with the conflicting descriptions for x86, it's because AT&T Unix already had a convention, and Intel was writing a fresh assembler and didn't respect that convention. With these old chips, you very often find that one book will use one ordering and a different book will use a different order. And so where you need to support multiple conventions is in building software that was written in one particular convention. The way that I'm supporting this for now is I'm just implementing multiple modules. You describe it once first as Intel and then again as AT&T. The way that I intend to support this in the long term is by assembling the program while holding the comments along, and then disassembling it using the different language definition so that I'm able to move from an older implementation of a language to a newer one. Or in this case, I could implement once for AT&T and once for Intel, and then move back and forth between them by rewriting the assembly source code, rather than having to rewrite the whole project. It's not a particularly elegant solution, but I've yet to come up with a better one. And if I could nerd snipe you, I really need a volunteer to implement the mod RM field. And I think it's only going to take you like 10 or 20 years. Any other questions?
So you've said that you've set like multiple times for about 2 hours just to create support for one variation of some assembly language, right? So how many did you manage to support up until now?
I think I have about 10 completed and maybe 2 or 3 that are partial. Where I have the partial ones is where I've not been able to figure everything out from the documentation. Like the Game Boy game that I showed you, that is an architecture called TLCS 47. And I had to import the Japanese manual for that chip before I had any code examples at all. And now that I finally have those code examples, I can't read the comments because I can't read Japanese. Prior to that, I had the instruction definitions, but no actual program examples. So I sort of know what everything is supposed to do, but there were ambiguities. Like, are the interrupts addresses or are they instructions? And I have no way to know because I have no complete program including the interrupts table. The 2-hour description holds accurate for a rather standard 8-bit microcontroller, or maybe a 4-bit microcontroller. Where you start having trouble is when a fancy feature gets added. Like the exclamation points in ARM assembly that describe that the condition codes won't be changed. Or in x86 you have the mod RM field, which our friend here has so graciously agreed to implement and send as a pull request at some point in the next 2 decades. Those pieces can take quite a long time to implement just by virtue of being complex and hard. Wherever your language does not support them, you can sit down in a coffee house and copy the documentation verbatim, and within an hour or 2 have a complete and tested implementation with no overlapping instructions, no ambiguous bytes or bits, and working labels and all the other features. Oh. Yes?
Hello. So what would you recommend as like a first, good step to getting into all of this? Like, I don't know, some microcontroller or whatever.
So when you're working with microcontrollers, and assembly language in particular, it is very easy to read about them without the details mattering. And if the details don't matter, it's not going to stick. So what you really need to do is to have a project that requires it. I can't play video games in the same way that some people shouldn't drink alcohol or snort cocaine. So video games would be the wrong way for me to get into them. But if you play video games and you have a particular antique game that you like a Game Boy, you can take your favorite game for the Game Boy and disassemble it and begin figuring out what it does. And you can then change it in order to see if you add cheat codes to the game. Like Zelda, for example, has a function that is called whenever you get hit by an enemy and you lose half of a heart. You can patch that to make your little Zelda dude immortal by never losing hearts. And in order to do that, you have to understand the code well enough to figure out where the right piece is and to make the change. And in doing that, the language becomes a real language to you that you can express meaningful things in, rather than just being a theoretical thing or something that you might understand in the abstract. So wherever possible, try to make a concrete project out of the microcontroller. And once you do that a few times, you'll be able to very quickly catch up the next few times. Cool. Yes?
Thank you. How do you deal with undocumented instructions? Did you find many of them during the project?
So undocumented instructions are a great question. There are a couple of projects in which all of the instructions are undocumented. Like the calculator I showed you, the earliest one in that series used an undocumented chip. There was documentation at some point in history, but it's been lost and no one has been able to find it. The instruction set has been reverse engineered, and the reverse engineering is not quite complete. It's good enough to emulate the calculator, but not all of the pieces are known. Like the Intel AT&T question, no one knows what order the operands are supposed to come in the assembly code because it all had to be figured out retrospectively. If someday we find the documentation, it will disagree with mine. But I'm reasonably well able to work with whatever documentation I have, and the errors that I have are at those borders where it's undocumented. Maybe I don't know all of the side effects, maybe I don't know what one of the opcodes does, but I can leave that as an instruction called to do or fix me, and still be able to understand the math routines of the calculator or how to write a game for it. All right, and I think we're out of time, but I have a beer and a club mate, and I will be around for the rest of the evening if there are any questions one-on-one. Thank you kindly for your time and attention.